So we have looked at the truss element, and we have looked at the general way in which the global stiffness matrix of the super element, which is the entire structure, is formulated out of individual truss elements, which are then assembled at their respective positions by the assembly procedure that we have learned. And finally, we get this global stiffness matrix K. This is the equation of motion of the super element or the entire structure formulated out of the element stiffnesses. The way we have formulated the element stiffness of the truss is pretty much the way in which it was done towards the beginning of the development of the finite element method. We have used the basic definition of stiffness element Kij. So what does it mean? So if I write the ith row of this, I can write it like j equal to 1 to n, where n is the size, n is the number of degrees of freedom. Kij uj is equal to fi. This is how I can write this matrix equation, the ith row of this matrix equation. So obviously I goes from 1 to n as well. Now imagine that only uj is equal to 1 and all other ui is equal to 0. Then this summation symbol drops out, and this is 1. So Kij is the force at degree of freedom I due to unit degree of freedom value at j. So that is the basic definition which we have used to formulate the element stiffness matrix, and then of course assemble it into the global stiffness matrix. Now we are going to use this basic definition to now derive the stiffness matrix from first principles for a beam element. The way we define a beam element is like this. A beam cannot undergo extension in the XL direction. The beam cannot extend or contract in the XL direction. Remember, the truss can only extend or contract in the XL direction. The beam can suffer transverse displacements. So it can suffer displacements in the YL direction, and it can also rotate. It can also take transverse loads and rotate. And therefore, for a two-noded beam element, the degrees of freedom that we choose are the vertical displacement V1 and V2 of the nodes, and the rotations θ1 and θ2 at the nodes. So there are 4 degrees of freedom in the beam element, and these degrees of freedom are V1 θ1, V2 θ2, and these constitute the vector of the degrees of freedom. This is a rotational degree of freedom. This is a translational degree of freedom. Note here that unlike the truss, we don't have U1 and U2 as degrees of freedom in this case. U1 and U2 are displacements in the XL direction, as we had discussed in case of the truss. And since this cannot deform in the XL direction, it does not have that capability, we do not include this. We'll come back to this point later. Now, the vertical displacements are V, and the rotations theta are derivatives of V with respect to the XL direction. So, but these are taken to be independent variables, and these 4 constitute the degrees of freedom. And corresponding to these degrees of freedom, there are 2 shear forces corresponding to V1 and V2, and there are 2 moments corresponding to θ1 and θ2. So the force vector is F1, M1, F2, M2. Remember, the sequence here has to match with the sequence here, in the sense that θ1 should correspond to M1, θ2 should to M2, V1 to F1, and so on. So in the local coordinate system, in this local coordinate system XLYL, our stiffness matrix, which will connect U with F. So the local stiffness matrix which will connect U to F should be 4 cross 4, because this is 4 cross 1 and this is 4 cross 1 as well. So the local stiffness matrix must be 4 cross 4, and we are going to derive the local stiffness matrix from the basic definition of a stiffness matrix, which is the due to a unit displacement applied at degree of freedom J, the force that you get at degree of freedom I is the stiffness element Klij. So by our basic definition, KL11 will be the force at degree of freedom 1 due to a unit displacement. So the first degree of freedom is a displacement in the vertical direction. So I give a unit displacement in the vertical direction, and the force that I need to do that uh, in the vertical direction, same vertical direction, will give me KL11 when all other degrees of freedom, theta 1, V2, theta 2, all are fixed. In other words, I am trying to um, deform this element in this fashion. So deform this element in this fashion, where this is a unit displacement, and of course to cause this unit displacement I need to apply a force which is F1, and all other degrees of freedom, theta 1, which is the slope here, is 0. V2 is fixed, so both V2 and theta 2 as well are 0. So to make this deformation possible, what is the F1 necessary? So I can give a displacement of, let's say, V1 here, and then my KL11 will simply be the force due to um, force per unit displacement in the one direction. KL11 will be F1 by V1, and uh, we will try to see how much F1 is needed to get a V1. This is possible because we are doing a linear problem. So instead of applying a unit displacement, we can apply an arbitrary displacement V1 and then just scale F1 by V1 to get KL11. Okay, so to solve this problem, remember that we will of course need a moment to hold the slope fixed here. We will also need a force and the moment to hold this point fixed and the rotation to 0. So those forces and moments we don't need to calculate in order to get KL11. All we need to calculate is F1, the force that is needed to deform it like this. But remember, there are other forces and other moments which will be used for calculating the other elements of the element stiffness matrix. So now let us try and calculate KL11. So to calculate KL11, we solve the beam equation. You would recognize this as the beam equation that you did in your strength of materials courses. And now let the length of this beam element be L, and this is equal to 0 because there's no transverse load. There's no transverse load applied like this kind of a load is not there in our beam element. It's a beam without any load, so this side is 0, and the solution to this fourth order uh, simple ordinary differential equation is Vxl equal to this, where C1, C2, C3, C4 are constants, which we have to determine from the boundary conditions. What are the boundary conditions? The boundary conditions are V1 at 0. So I have taken the origin here. So V1 at 0 and theta 1 at 0 is 0. Then V2 is 0 and theta 2 is equal to 0. So V is equal to, at x equal to L, theta is equal to 0, which gives dV dxl equal to 0. Remember, theta is derivative of this. So if you take dV dxl, you will get half c1 xl square plus c2 xl plus c3. At xl equal to 0, these are 0, this is 0 as well at xl equal to 0, and this implies c3 is equal to 0. At xl equal to l, dv dxl at xl equal to l is half c1l square plus c2l, and v is equal to 1/6 c1l cube plus half c2l square, c3 0 plus c4. Okay, so this is 0 at x equal to l, this is 0 as well. So from here you can now solve for two of the constants. So you can solve for so we get these relations between the constants. We get c1l. From here we get c1l equal to minus 2 c2. So this is it. And then using this, from here we get c4 is equal to minus 1/6 c2l square. You can work that out. So one more boundary condition is required to determine the four constants, and that boundary condition that we use is that the shear force at this point, F1, is equal to F1. The shear force at this point is equal to F1. Now remember that in our case, there's no transverse load, so QXL is equal to 0. But this equation actually is EI d4V dxl4 equal to Q. This is what this equation actually is. And you also remember that dv dx is equal to Q, and then dm dx is equal to V. This V is the shear force, so Vxl, and this is also Vxl. This is the shear force. Don't confuse it with the vertical displacement. So now if that is the case, then Vxl, V at xl is obviously EI dqv. This is the displacement V, dxl q. So this is equal to, at xl equal to 0, this is equal to V at xl equal to 0 is, we take it to be equal to F1. Now also remember that at xl equal to 0, V is equal to V1, the degree of freedom at this first node. But first let us see what this equation gives us. So we take three derivatives here. We take dv dx, which we have dv dxl, which was half c1 xl square plus c2 xl plus c3. We have d square v dxl l square, which is c1 xl plus c2, and then d3v dxl cube is equal to c1. So at xl equal to 0, c1 is equal to f1 by ei. So c1 is f1 by ei all over. At xl equal to 0, v is equal to v1, which is in turn equal to c4. Now to calculate c4, we have to go back to here. So c1 is f1 ei times L, which is equal to minus 2 c2. So c2 is minus f1 by 2 ei, and then c4 is c2l square. So this is equal to minus of 1/6, again minus of f1 by ei. This is this is F1 by EI into L, and then you have another L square here. So this is F1 by 2 EI L. So this is equal to 1/12 F1 L cube by EI, that is equal to your V1, which is equal to C4. So V1 is C4, so this is equal to 1/12 F1 L cube by EI, and KL11, remember, can be obtained as the shear force in degree of freedom 1, that is in the vertical direction, divided by the degree of freedom value at the same node, F1 by V1. So if I do F1 by V1, I get KL11 is equal to 12 EI by L cube. So I have got one component of my stiffness matrix, that is KL11, using entirely first principles. Okay, so now we will carry on this procedure and find some more components of the stiffness matrix.